Hi everyone, my name is Ryu.
And I'm Minto.
We're from San Jose State University and we will present to you about lead-free MEMS device as part of our topic review project for EE, MatE, and ME 169. So here's a quick overview. We will start with an introduction about background on lead and the two materials we studied to replace lead, and the details on the two technologies, and we'll conclude with the forecast on the two materials. So lead has been a very popular material for electronic device industry, namely for packaging and other uses. Lead has a very high electrical conductivity despite having a very low melting temperature compared to other materials with similar electrical conductivity like copper, gold, or aluminum, which allows a wide range of material compatibility. For example, use of polymer in electronics packaging. And lead is much cheaper compared to the other metals I just mentioned, so everybody wants everything cheaper, so why not? But as we know, lead is very hazardous during its processing, use, and disposal. During processing and use, there is a lot of health hazards associated with lead. We would like to focus on health hazards related to lead during its use. For example, in biomedical devices, if any lead is used at all. For example, we will discuss a bio-MEMS device, implantable bio-MEMS device, and you definitely don't want lead in an implantable device. Or if you have it, you don't want it leaching out at all, but lead leaching out is a significant issue that the industry has been facing. And disposal of lead is very unfriendly to the environment. For this reason, many countries in Europe and Asia have banned use of lead in many devices. So there are many groups that are making effort to replace lead in the electronic devices. And the two materials that we studied that has the potential to replace lead are gold-copper sealing with indium interlayer and sodium-potassium niobate tantalate. For short, it will be NKNT, with bismuth ferrite dopant as a thin film on piezoelectric material. And MT is going to take over and talk a little bit about the gold-copper seal ring.
So seal rings are used for packaging of circular openings that are usually found in MEMS devices. And they are mostly common in implantable devices because they are tubular. Because they are tubular or have circular input and output. Gold and copper were chosen because of their emerging popularity in MEMS industry. Indium interlayers were placed between gold and copper to form gold, indium, and copper indium intermetallic phase, which is mechanically and thermally stable. The group studied the effects of processing parameters on the mechanical performance of seal rings. So I'll discuss about the processing of gold and copper. First, photolithography was used to get pattern on gold part, and then the gold part is hot pressed and ring-shaped indium foil and copper substrate to form a seal ring like the pictures shown on the right side. And the effect of temperatures and pressures on the mechanical performance were investigated at 450 and 500 K temperatures and at 0.5 and 0.7 megapascal. And here the results. The pictures show that at higher temperatures and pressure, it will result stronger ring seal.
Alright, and I'll talk a little bit about NKNT bismuth ferrite piezoelectric vibration energy harvesting device. Traditionally, lead zirconate titanate has been a very popular piezoelectric ceramic. It is actually used in one of the AFM devices that we have on campus as well. but as I said, people want to get rid of lead as much as they can. So this group in particular studied NKNT piezoelectric device, excuse me, with bismuth ferrite dopant during sintering. Bismuth ferrite was used as a dopant since it helps to form a denser microstructure, which improves both mechanical and piezoelectric behavior of the material. As you can see in the figure A and C on the left, without the bismuth ferrite, the microstructure formed by NKNT is very porous, and these pores will act as stress concentrator during its use, and it will also inhibit some of the electrical properties. And since it is a vibrating device, we would like to reduce the amount of stress concentrators, and in the image, in the span of about 1,000 to 2,000 nanometers, you could already see enough pores that would cause failure in the device. However, once doped with bismuth ferrite, as shown in figure B and D, the microstructures formed are much denser, and this resulted in stronger material and improved electrical properties. On figure A, you see a much higher dielectric constant in the bismuth ferrite doped NKNT film compared with the non-doped material. Likewise, there was a much lower leakage current density in the bismuth ferrite doped film. And the forecast of the two materials, well, although these studies were done, there has to be much more research needed to optimize the cost and material availability. For example, lead is much cheaper, as I mentioned earlier, and is more commonly found when you compare it with copper or gold. And also the properties and the processing parameters of metals like copper and gold were much higher. When you compare it with lead, it was at about 400 to 500 Kelvin. That is almost 100 to 200 Kelvin higher in processing temperature when you compare it with lead MEMS devices. So this will lead to compatibility issues with the already existing devices, since polymers that they currently use are designed for temperature range for lead, not copper or gold. So much study and effort is needed to commercialize lead-free MEMS device. And here are the references to the two groups we used for our presentation. I hope you enjoyed our presentation, and thank you for listening.